Justin Miller, Oxford College Physics here, and we are going to get things flowing. Oh yeah. So what I want to talk about now is electrical current, which generally is the flow of charge, which even more generally is the flow of electrons in our everyday household electronic systems. So what do we have here? Well, we've got electrical current. Again, the flow of charge can be utilized to do things that we want it to do. We have electrical motors, right? Those electric motors. How do we get something to start turning with electricity? We'll get to that. We got lights. Hey, the lights, they require some electricity, right? We flip on a switch, we push a button, the light goes on. What's going on? Well, it's due to electrons. Electrons that are flowing in the circuit. Now, they could be flowing overall in some uniform direction. They could be vibrating back and forth, but there's motion involved with the individual charge carriers, which again, generally speaking, is going to be electrons. Really, current can be due to the motion of positive charges too, so we can have some sort of cationic substance in which positive charges can flow around, but we're going to stick with electrons. So, electrical current. Is flow of charge. And we'll just go ahead and put electrons. So what we're going to do is sort of house current inside wires, some sort of conductive pathway for them to navigate through and do our bidding. So we generally confine currents to some sort of conductive pathway. Such as wires. We can always have just some little thin beads. You can still kind of say that they're wires. There's some sort of conductive pathway. Why do we need a conductive pathway? Because electrons can move around in conductive pathways, right? They can move when they are under the influence of some electrical field. So we got the conduction electrons, and a conductive material can react to an electric field that's within that conductive material and move due to it. So that's kind of what we're looking at here. We got some conduction electrons and they are interacting with an electric field. So what we want to do is sort of understand what's going on and come up with some sort of general notion of how much current is produced for a given system and what really dictates how much current you get out of something. So let us first define current. We define current or a constant, I'll put here, constant or average value as I. We'll use capital I for current, and that is going to be a delta Q divided by a delta T. Delta Q is the amount of charge that passes through some area of cross-section to say passes through a given point. Time delta T. So if we look at units of this, the units of current are going to be, well, what's the units of charge? Coulombs. What's the units of time? Seconds. coulombs per second, which we have capital C over S, which we go ahead and say, you know what, let's call that something else because we're going to use it a lot. We're just going to call that amps. A. 1 amp is 1 coulomb of charge passing through a point every second. How much is 1 coulomb of charge? Well, how many electrons? Something like that. To get a kind of idea of what we're talking about here. Well, 1 coulomb of electrons is of the order of 10 to the 18th electrons. How is that? Each electron has a charge of 1.602 times 10 to the negative 19 coulombs. Take the inverse of that, you get how many electrons there are in 1 coulomb. And it's a whole bunch. But there we go. That's how many conduction electrons would be passing through a point in 1 second if we had 1 amp. 1 amp of charge. Excuse me, 1 amp of current. So there we go. Well, what else do we got here? Well, we should go ahead and say the current may be varying with time. True, not tour. The true definition is I is equal to dq dt. The rate at which charge changes with respect to time, and that is at a given point in a wire or a circuit or something like that. So this is actually the definition of current, dq dt, time rate of change of charge. I'm not doing calculus, don't worry about this. A lot of times we'll be dealing with constant currents anyway, so, but here and there we may invoke that. That's what we've got going on. All right, so we got some amps. So how do we get these conduction electrons to start moving? Already alluded to that. We use an electric field, right? Hey, electrons will move in the presence of an electric field if there's nothing else there binding them to locations. So we talk about the conduction electrons. We have an electric field. Yeah, the conduction electrons are going to move around. So how do we get that to be housed within some conductive pathway? Well, when a conductive material like copper wire is connected to the terminals of a battery or power supply, whatever we want, just use batteries. The potential difference due to the source is now extended across conductive material. This means that there must be an electric field that is set up within the material. So that's what ends up happening. We've got the potential difference across the terminals. We connect the terminals via some conductive wire. And what happens? Well, it sets up an electric field such that the potential difference across the terminals is now the potential difference across the ends of the wires as well. And well, if that has to be the case, then there has to be an electric field associated with that, because we already know potential differences are directly correlated with electric fields and displacements within that field. And thus, this is what we got. Now, generally what we have is the electric field is fairly near, this is an approximation, but fairly near uniform in terms of its magnitude. Obviously the direction varies with the contour of the actual conductive material, but if we're just talking about a nice thin wire, we connect one side to plus, one side to minus, the electric field goes from plus to minus and is constant in its magnitude throughout that wire. And that's kind of how things work out there. So what else can we do with this? Well, we just take this, right? Let's take a little battery. Plus, minus, battery, and then we'll take a wire. And say, you know what, I'm going to take some conductive wire. This, connect it plus to minus. And what happens? Well, the second that we connect it to both ends, or both sides of the terminal, we will get the electrons start moving. The conduction electrons that are within the wire already. So the electrons aren't coming from this battery. The battery is the source of potential difference. The current is due to the electrons that are already there in the conductive material. So which way are electrons going to want to go? Well, we've got the electric field's going to go from plus to minus. Electrons want to go in the opposite direction of the electric field. They are repelled by this minus and attracted to this plus. So the electrons want to go around this way. That is the electron current. And, well, it goes from the minus potential, or from low potential to high potential. That's it. That's it. So, depending on the potential difference across the terminals, we will get varying amounts of current. We find that if we increase the potential difference, we use, instead of a 12-volt battery, a 24-volt battery, hey, we get more current. That there's a direct proportionality between those things. So that leads us to define another quantity, because it turns out that the current itself is correlated again with the potential difference of the source, but it's also correlated with the material, the conductive material, how long that conductive material is, what its cross-sectional area is. There's all sorts of things that go into that. So, let us just do this. We note that as the potential difference of the source is increased, the current in the system increases as well. So what can we do? Let us define another quantity. Let us define resistance, which is the measure of the measure of the opposition to current. And we define resistance as delta V sub R divided by I. It is the potential difference across whatever we're defining the resistance of to the current that's going through that portion. And that ratio defines us the resistance of that material for that particular association. Now, what we have for certain materials, generally called ohmic materials, we have that the resistance is pretty constant. That this ratio here we increase this, this increases as well, such that the ratio always defines the same quantity. And not all materials behave like that, but a lot of them do, ohmic materials. And well, that's nice because we can sort of get a one-to-one effect. We go ahead and we double the potential difference across that section of wire, we're going to double the current in it, such that the resistance of this section here is a constant value. And that's nice to be able to do. And that's why we care to define resistance in this particular way. Because a lot of materials behave like that. Not all, but a lot. We now introduce Ohm's law. Mr. Ohm did some good stuff. Mr. Ohm said, well, delta V is equal to I times R, which is really just a recorrelation of this, taking the definition of resistance as that ratio and reformulating this. So what do we have of this? Well, delta V is potential difference across a section of material which has a current I and a resistance R. So that's it. So what we're going to do with this is sort of start to go into some circuitry, but there's some more things that we need to point out here. Number one, we've got resistance. What are the units of resistance going to be? Well, if we go back up to the definition here, it has to be volts per amp. But instead of calling it volts per amp, we're going to call it ohms. Talk about so many ohms of resistance. And for that, we use Greek symbol omega. So this will be what we utilize for the unitization of resistance. This nice symbol here. Let's say it's 100 ohms or 1,000 ohms or 5 ohms. And that just, again, is a measurement of the opposition to current in that given section of material, whatever it is. And that's it. All right, so we've got that going on. There's one other thing that we want to be a little bit careful of, and this has to do with the direction of the current. This is the true direction that the electrons are actually moving in a circuit, or in this wire. They go from the low potential side to the high potential side. However, as convention has it, we do not measure the electron current. We measure the current that is said to be in the opposite direction. You may say, well, what does that mean? How can there be a current in the opposite direction if it's the electrons that are moving? And I say, correct. That's a really good question. So it turns out that it's just sort of embedded in the lingo at this point, that when we talk about current, we're talking about an assumed sort of positive charge flow, even though that's not the case. It's negative charges are the charge carriers in our everyday circuits here. So even though we say that there's this current, which we call the conventional current, the conventional current is in opposite direction. The magnitude's the same, the how much. And actually, hey, there is no true conventional current. We don't have positive charges moving from here to here and cycling around this way. It is the electron cycling this way, but measurement-wise, you start using multimeters, things like that, they measure conventional current. So it's just easier in the end to sort of accept that and say, okay, we're going to say the current goes from high potential to low potential. And that makes things easier anyway. Let's think about, oh, it wants to go from high to low. like something if I drop it wants to go from high to low. So even though it's false, it still works out fine. There's no real consequence other than it produces a little bit of confusion in the beginning. But unless we state otherwise that we want specifically the electron current, we're just going to be working with the conventional current and assuming that it has the same amount of current as the electron current, it just flows in the opposite direction. No consequence other than that. All right, so this is what we've got going on there. So now we're going to introduce something else, and that is a resistor. Now, introduce a circuit element called a resistor. A resistor introduces some measurable resistance into a circuit and can be used to control the current. That's what we want to be able to do. We want to be able to dictate how much current is in what section of a circuit, given that we hook it up to a certain source potential. How do we do that? Well, we introduce resistors, which are just little circuit elements that are made of some conductive material that have a certain amount of resistance that then control the current. All right, give me 1 second. What do resistors look like? Well, they're pretty simplistic looking. They come in various shapes and sizes, but generally they're just some little element like this. It has 2 terminals so that you can hook it up in a circuit. It has this interior part, this little cylindrical part, that actually has a certain type of material with a certain length and a certain area of cross-section, what gives this resistor its overall resistance. Which this one, I believe this is 680 ohms. 680, yes, 680 ohms. And then we got something else. Hey, it looks similar. It looks a little bit different. You know, the ends are kind of curved up. That's okay. Those are just someone bent those. This one has a resistance of 470 ohms. Which one, when hooked up to, say, the same source potential, is going to allow for a greater amount of current? The resistor with the least resistance. This one produces a lower amount of opposition to current, and thus the current will be greater in the circuit if I stick it in here than if I stuck this 680 ohm resistor in. So lower resistance, greater amount of current is a general rule there. All right, so any type of wire conductive pathway has some finite amount of resistance under normal circumstances. Generally, connective wire between the positive terminal and the negative terminal for just some alligator clips has a very, very low resistance, maybe an ohm, 1 ohm. But we can kind of combine the resistance of conductive pathways and resistors into one bulk amount of resistance and just say that that's the overall resistance of the circuit. We call that some resistance R, or to say we have a resistor of substantial resistance, and we're just going to say, hey, there it is in the circuit. It's the overall resistance. Here we go. So, a resistor symbolized as this. It's like an obstruction, is what you can think of it as. So this is one side, this is the other side. Those are kind of the terminals of the resistor. And this represents the actual resistor that has some resistance R measured in ohms. So what do we do with this? Well, there's the circuit element. This is like conductive pathways. And when we go ahead, just come over here, when we go ahead and stick a singular resistor into a circuit connected to some source potential, what does that look like? Circuit diagram wise, this. A singular resistor circuit diagram. Shown as, well, we got our source potential. Look at this. Got our source potential, got the plus side, got the minus side, and then we've got our resistor. And what else are we going to have in this? Well, once this resistor is hooked up to the source potential, the positive and negative terminals of it, we're going to have a current in there too. So what do we have in terms of the direction of the current? Conventional current is what we're going to stick with. So conventional current goes from high potential to low potential. How much current? Well, that depends on what the source potential is and the resistance of the resistor. Now, if we go ahead and assume that these conductive pathways between the resistor and the terminal have a negligible resistance, or we're just adding it into the overall resistance of the resistor, well, we'll have that the current through the resistor is then, it's gotten by Ohm's law. Should I erase Ohm's law? We have the current up there. This will be the resistance. And we'll have that I is going to be equal to delta V. We will not put delta V. We will put source potential divided by the resistance. Because we'll assume that the potential difference delta V sub R is equal to that of the source. Wow, this is like the positive side, an extension of this. This is the negative side, extension of the negative terminal. Again, we're going to go ahead and say that this conductive pathway here, these branches have negligible resistance, and this is what we get. Boom! So there's the current in the circuit. Current I is dictated by the resistance of the resistor and the potential difference of the source. Very cool, very cool, and pretty simple too. We want less current? Say, oh shoot, we got too much current. That's gonna do something bad. We can increase the resistance. How? We put in a different resistor that has a higher resistance. Or we enter in another resistor. We'll get into that. But anyways, that's what we've got going on. Delta V is equal to IR, so the potential difference across the resistor is equal to the current through the resistor multiplied by the resistance of the resistor. And for a singular resistor hooked up to a source potential, DC source potential, we have that current is going to be given by this. All right, so what else can we do? Well, we can go a little bit further with this and say, okay, so how do we go ahead and build ourselves a resistor with a particular resistance? Well, again, if I opened up one of those little cylinders here, opened up one of these, I would find that there would be some pretty large windings of some wire in here. It could go like this, or it could go like this. It'd be like a little spool almost, a spool of wire. And it may be very, very thin, or it may not be. It just depends. And it actually may be made out of a different material than copper. Any conductive material will do, but depending on what material it's made out of, the length of that material and the cross-sectional area of that material, we will get different amounts of resistance. So let's talk about the length first. The resistance of a resistor correlates with the length of the material used to produce or to build that resistor. Why? Well, the longer the section is that the electrons have to move through, the more opposition they run into. What's the opposition due to? They've got to navigate through the material. They've got to navigate around the other bound electrons and the protons. It's not like it's just empty space. They've got to make their way through this conductive material. And, well, that's a matter of them making it through, navigating around. So, the longer that section of material is, the greater amount of navigation that needs to take place, the greater amount of resistance that there is. So, the resistance of some material is proportional to the length of that material. So what about the area of cross-section? Well, think about this. You take yourself a tube from an empty spool of paper towels. You take a big breath. You blow it all out through that tube. How fast can you do that? How long does it take you to get all of the air out of your lungs through that tube? You measure it. You say, I don't know how long. Well, let's do this then. Instead of using a tube, you're going to take the same deep breath, but you're going to take a little straw. And you're going to try to blow all the same amount of air out of that straw in the same amount of time that you blew it out the tube. That's going to be really hard to do. Why? Because the straw is a lot thinner. It doesn't allow as much to go through per unit time without extra effort. So, that area of cross-section has something to do with how many electrons we can really pack through a given length of material per unit time. The smaller the area of cross-section, and the harder it is to force electrons through it, to get electrons to go through. There it is. So we find that the resistance of a given length of material is inversely proportional to the area of cross-section. As it's reduced, right, the resistance of that section gets larger. And there's one other factor. Well, the other factor is the material that you're using. And it comes down to conductivity, the number of conduction electrons per unit atom, material properties. How conductive is the material? Well, instead of using conductivity, we use what is known as resistivity, and say that every material has a certain resistivity that's based upon correlations of conductivity, which again kind of comes back down to number of conduction electrons per unit atom. Anyways, depending on the material, you have different resistivities. And we can just kind of come up with that and say, hey, this material has a resistivity of this material has a resistivity of this, and we can start utilizing lengths of that material, certain cross-sectional areas, and building resistors with certain resistances. So that's what we do. The resistance of a resistor, or a length, some material, is determined by the length cross-sectional area and a material property called resistivity. R is equal to rho times L divided by A. Rho is this right here, RHO, is the resistivity of the material. L is the length of the material, and A is the area of cross section. So this is how we build resistors. Use a certain material, a certain length of it, a certain area of cross section, boom. You want to build a 100 ohm resistor with a certain length, a certain area of cross section, and a certain material, figure it out. Figure it out. There it is. So that's pretty much what we've got going on with resistors, resistance, and Ohm's law. Primarily what we wanted to get, current, the correlation. So we'll leave it at that for right now. We'll come back, we'll do a lot more stuff with this, and yeah, good times. Do not resist. Never mind, I couldn't resist. Take care, see you next time.